you can use this dev kit and the language to run a simulator of a quantum computer, and you can run that, download and run that on your laptop, or through Azure, you can run that on real quantum computers.
You were a quantum physicist at Yale. How did you get interested in that?
I fell in love with physics in high school. I had a really special high school experience. I went to a small all-girls Catholic high school in Nebraska, and I had this amazing physics teacher for my junior and senior year who taught physics and in an AP physics class. And it just captured my imagination, the idea that you could have a framework and a set of equations that described and helped you understand the way that the world worked, and that you could actually then go build stuff and measure it in the real world was super fascinating to me.
So a teacher had a large impact on your life.
Absolutely.
So then you go to Yale. What did you get to work on in the lab?
Well, I started out at MIT, and right when I got there, I met someone who had just come back from a summer at CERN doing particle physics experiments. And that was the most exciting thing I could possibly think of to do. And so I said, okay, that's my goal. And so I went and joined a lab, and I started out in high energy nuclear and particle physics, building detectors and designing particle detectors that would eventually end up on the space station. And that was super fun. But the end of my time at MIT, I had taken every class in quantum mechanics that they had. And they offered for the first time in the graduate school a seminar class on quantum computing. And it brought these two areas that I was interested in together. And I took that, and that changed the path of my studies. And that's how I ended up at Yale and doing work in quantum computing and quantum physics.
And then you have this jump, like I'm looking at your stuff, and you've got this jump of all this quantum computing in Yale and MIT. And then you go into corporate strategy. I was like, well, how did that happen? She must have seen everybody like partying and making a ton of money. She's like, I'm going to go over there because I know I can be really smart over there and make a ton of money.
Not exactly. But the way that jump happened, because it does look like a discontinuity in my resume and in my experience. The way that happened was I was doing my work at Yale. And at that point, quantum computing was super exciting. I'd seen the promise of what this technology could do and the impact that it could have on the planet. But at that time, when I was finishing up my degree, it felt really, really far away. And it was this amazing promise of, if we could build a quantum computer, we could do these amazing things, like solve some problems exponentially faster. But at that time, it felt really, really far away. We could make 1 and 2 qubit systems. We couldn't make them. One of the key issues with qubits, or these building blocks for the quantum computer, is that they have any interaction with the environment. It measures the quantum state, and we lose the quantum information. So we couldn't get them to stay quantum very long. For me, it was hard to imagine this path to scalability in terms of having enough that you could do something interesting in it. And so at that point, quantum computing still felt really, really far away and was a big if. And I felt like I needed to get a broader set of skills, and I saw myself more on the productization side of things. And I felt like I needed to get a broader set of skills to do the type of work I wanted to do and have the impact I wanted to have. And I went to McKinsey and did work primarily in semiconductor manufacturing. So I went from the academic clean room into industrial clean rooms and helping semiconductor companies, helping them with all elements of their business. And so from that perspective, it was a huge jump going from an academic research lab into the heart of corporate America. But it was, from a work perspective and a content perspective, it wasn't as radical as it seemed, or it could seem from the outside.
Yeah, I jump around a lot. I got into software really young, and I started building software. And then the thing that fascinated me was getting to learn an entire business. I would learn the entire insurance business, build an insurance software. Then I'd learn the entire fitness business. And that variety of learning the business really kept me energized and excited about what I was doing, which is super important. You're getting to do quantum physics. Like, I have so many questions for you, but first, can you tell me, like, what do you do at Microsoft with Azure Quantum?
Well, so with Azure Quantum, we're really bringing this technology to developers. So we're hoping you get your hands on it. And so my role at Microsoft is I run program management for the quantum program, and this spans everything from the qubits that we're building to the control systems, to the cloud platforms, and everything in between. And so with Azure Quantum, we're really bringing this technology that we're building. We have an open source programming language called Q#. We have a quantum development kit. And we're bringing those together with the power of Azure to make this open, accessible ecosystem to start, building and learning and playing with quantum technology. So you can use this. You can use this dev kit in the language to run a simulator of a quantum computer, and you can run that, download and run that on your laptop, or through Azure you can run that on real quantum computers from partners of ours. So we have trapped ion systems in there from Honeywell and IonQ. We're bringing superconducting qubits to that. And then a really exciting thing that we've discovered over the past few years on our team is that as we've learned about how quantum computers solve these interesting hard problems, we can use some of those techniques already on classical hardware. So the hardware that we already have in Azure. And we call those quantum inspired techniques. And we can use some of those properties and principles of quantum computing and quantum physics to accelerate problems using the hardware that we already have. And so we have capabilities for those quantum inspired tools already in Azure Quantum as well.
And so how did this all happen? Did Kevin Scott call you up and say, Julie, we need you. You're the quantum king. Like, we come do this with us. How did you get to Microsoft?
So I came to Microsoft originally out of McKinsey. So I went from Yale to McKinsey, and I came to Microsoft and did a variety of mostly corporate strategy roles, as you pointed out earlier, working across all of Microsoft's businesses. And then I took a role at Adobe, leading strategy for their creative business. But along the way, so where I didn't have a discontinuity is I'd been helping friends and former colleagues from Yale start quantum computing companies. And so I'd been advising quantum startups, and I'd really kept up with that field. I have a lot of friends. It's a small field, and I have a lot of friends in the field. So I'd, stayed in that field, and I'd been kind of looking to see when I would do quantum computing again as my day job, instead of, on the side of the other things that I was doing. And there was a terrific opportunity at Microsoft to come back to Microsoft about going up on 4 years ago, to come back and lead business development for the quantum organization. And that was really, business development in kind of the most fundamental sense of thinking about, what would a business around quantum computing even look like, really understanding what customers needed from that, and creating kind of programs and products around that for enterprise customers, for startups, and for partners of ours, to really bridge the gap between, this new emerging technology that's coming online, and really making it so that we understand that true customer need for the technology, and guide our thinking and development of all of the pieces that need to come together to make this a reality.
Well, you sound like the perfect fit for the role. You've got this entrepreneurial business ninja experience, right? Helping with all these startups. Meanwhile, you have the subject matter expertise of the quantum. So you can connect the applicable business use cases today to wherever the technology's at as it matures, because you got to get that hook, that money, so that you can improve it and grow it. It's one of the hardest things to learn, but once you learn it, it's the most clear and obvious thing you have to do.
Well, thank you.
I want to know, all right, so we've got a lot of, CTOs, VPs of engineering, geeks that listen to the podcast, right? And so I was curious, because you're so deep in the quantum world, you've got other bright people out there that just don't spend time in it, right? They're in the computing world, but they're just not deep in the quantum. What's some of the misconceptions or the things that you would want to put out there and let them know?
Yeah, that's a great question. One of the things, I guess, is a kind of there's a couple of common misconceptions. One is that, I hear from some people that, quantum computing can solve any problem faster. That's an element where, really understanding what quantum computers can do and what they will be able to do. It's a harder problem than that, and it's an oversimplification. So first of all, it's, we're computing with really different building blocks, and they work in really different ways, and we have to program them differently. And so they're not, quantum computing is not going to solve every problem faster. One of our experts at Microsoft, and distinguished scientist is the title. And he says, on average, quantum computers will solve problems about 1 billion times slower for the average problem. And it's really finding these problems where you can take advantage of these quantum properties like superposition and entanglement, and using the wave-like nature of these particles to find problems where you get an exponential or, a polynomial speed up that's greater than quadratic. And then getting into the, really into the details of how that algorithm works, kind of all the things that we know how to do, classically. What's the IO? How many gate operations do we need? And getting into the details of that, because there's lots of places along the way where you could lose the quantum speed up that you thought you had. And so that's, one of the problems. And we see, clear areas where quantum computing is going to have an impact, areas like chemistry, material science, where you're high up on the periodic table, or you have a lot of what's called quantum correlations in molecules, or these problems are really, really big compute problems. And so that's kind of the first place. It's going to be, we're focused on areas where it's big compute, because that's where quantum can make a big difference. And so we hear a lot of problems that are really high performance computing problems, big data problems. And that's not where we're going to see the impact. And so I'd say, the first misconception is, this is going to solve everything faster. And the second misconception is, really getting into kind of unpacking this word faster, because that's also, the devil's in the details on how we make these things work and where those improvements are going to come from. So it's not just that we can solve every chemistry problem faster. It's where we have real bottlenecks in classical compute that send these runtimes into billions of years with all the compute power that we have. And it's, in the details of that. So if you think about problems in, say, drug discovery, we talk to a lot of pharmaceutical companies, and, for organic compounds where they can do those calculations using high performance computing, they're looking for higher throughput typically on those, on those simulations. And where quantum computers are really going to help is where we can get the energy accuracy to where we need it to design new compounds. And so if you think about the kind of average simulation for drug discovery, they're looking for increase in throughput. And what we often hear is they would trade off energy accuracy for increased throughput. And so that's not specifically where quantum computing can help. But an area where it could help is work, it's demonstrated in the work that we published last summer on, thinking about designing new catalysts. And one that's really exciting and top of mind for us from Microsoft, related to the pledges that we've made in carbon, is there have been, proposals for ruthenium-based catalysts for removing carbon dioxide from the atmosphere. But to design a catalyst that would be really efficient, you need to understand the energy levels of all of those intermediate reactions. So all that, that process where you have carbon dioxide interact with a catalyst, and it undergoes this chemical reaction where you spit out the catalyst again, and you have something valuable like methanol come out, and you consume the carbon dioxide. But to have efficiency in that catalyst, you need to understand those energy levels really, really accurately. So that's an example where quantum computing can help. And it takes that calculation from maybe hundreds of millions or billions of years on the computers that we have today into what we believe can be done on a quantum computer in about a month.
That's pretty cool. I was just listening to Elon Musk talk about the he's just announced $100 million prize for, have you heard about this?
I haven't, actually.
Oh, okay. So they're looking for new ways to extract carbon from the atmosphere. And because the current ways that we know about, there's enough problems with them, or they're not efficient enough. And he was describing how, carbon's, when it's in the atmosphere, it's in this low energy state, and trying to get it to rebind to something physical takes a lot of energy. And that's the problem that needs to be solved, which I think is what you were just discussing.
Exactly.
But he's got this contest going for $100 million, and we should form a team, and you should do all of the work. No, I'm just kidding. Feels like school again. But I think that's fascinating that he's out there advancing it, and he's not like waiting for this to happen. He's just saying, all right, here's $100 million. Let's find some better ways. I really like when him and Bill Gates and when these wealthy people who are, titans of their industry are doing things like this. They're helping humanity move forward.
It's so important. And we think about this every day, here at Microsoft and the work that we're doing, saying, we're building this incredible compute capability. Let's go solve the world's most pressing problems with this.
When am I going to be able to go to Best Buy or pull up my Amazon app and buy a quantum computer?
Well, you should pull up your Microsoft Azure account.
Oh, just kidding.
And I mean, you can use this today. So you can use this and start to do small experiments, with Azure Quantum today already. So I think, in terms of buying a quantum computer, I think that'll be a little bit further out. The quantum computers that we're building have to be run at millikelvin temperatures. So maybe not everyone's calibrated in millikelvin, but it's a few hundred times colder than deep space. So it's not something that most of us have lying around the house. So maybe a little while before you're buying that. But the more relevant thing is, think about what you're accessing through the apps on your phone. For a lot of this, you have some, front end interface on your phone, but you're accessing some massive cloud resource in the background, whether it's, something that's done with machine learning or, your movie repositories, all of that streaming to you from the cloud. And that's, for the foreseeable future, the natural way to access these quantum computers will be in the cloud. And this is going to evolve over time as we move from these, kind of small demonstration systems where we can learn and play and start to build and understand how to program these things. Programming looks really different when your bits are in superposition of 0 and 1, and you have to use things like quantum entanglement to get results. And those systems become much more powerful over time, up to the point where we have systems where we can reliably control the qubits, keep them long, quantum long enough to do interesting things, and have a system that scales up into the millions of qubits that we need to solve these problems, like designing new catalysts for carbon fixation.
I like that. Yes, definitely go to Azure if you want to play with the quantum playground thing that they have. I still want one in my office. I would just like one right here. Maybe I buy a used one on eBay or something, and it may not even turn on. But I just think it's so cool because it is the future. I mean, this is stuff that was being theorized 20, 30 years ago, and now we're seeing that it's reality, and it's fantastic, right?
It is. It's really, really exciting. And I think back, you talked about the seeming discontinuity in my career of going from this place of being in a university lab, thinking, if this question of if we could ever build a quantum computer, to now it's saying, we're looking at, when, asking the questions of when will we be able to solve these hard problems, and what are the pieces of engineering work that need to be done to be able to get there and put this into your hands to go solve these planetary scale problems.
When you're like out and about, right? Like at a restaurant or with family and you're meeting new people, how do you explain to them what you do?
Well, when we used to do that, go out and about.
Yeah. Back in the day.
Back in the day. Yeah, it's a good question. I'm trying to think. I get a lot of questions from my kids too, about, what is quantum computing and what do we do? It really depends on who I'm talking to. Certainly how I describe it.
Or if you want to talk.
Yeah. But it's, at the heart of it, it's figuring out new ways to solve these really hard problems. And it's, at the heart of it, that's been, one of the things that's been continuous along my whole career is really tackling hard problems. And it's, for me, that's tied deeply into scientific method and my training as a scientist. But figuring out how to solve these new problems, because all of the technology, well, it's super interesting, and there's tons of really fascinating physics in every aspect of what we're doing. The real value of any of this technology is what you can do with it. And so, really understanding, think about what I do and our team here at Microsoft is really understanding what are these hard problems to go solve, and then how do we, assemble all of the building blocks and put that together into an integrated system to solve those real problems. And there's lots of elements of that. It's, really deeply understanding the problem, matchmaking that with the technology and understanding, can our capabilities help improving our understanding of what those problems are? And then building, to really deliver the system, the underlying quantum physics and the qubits or the building blocks of these, that's one small part of building this integrated system. We have to control it. We need programming languages. We need new types of compilers, runtime, building the cloud ecosystem, building the services to make it accessible by the people who understand these deep problem domains. And so it's really figuring out, all of those pieces and putting them together in the right way to get to those solutions. And so I guess that's how I describe what I do.
Yeah, organizing people to achieve outcomes, right? Now, here's what I want to know, because I'm an entrepreneur. I've owned several businesses. I currently own a business. And so I'm always interested and fascinated to talk to other people. You're essentially acting as a business owner because you have this business unit, right? And so I'm always fascinated by team structures and things of that nature. And what I'm hearing you say is that you have to have a deep understanding of these domain specific languages, essentially. And you have to be able to think that there might be a potential. I talked to a customer, right? You said that earlier, and they were talking about throughput versus, I believe, energy density. And then you figured out that it wasn't a good applicable use, right? So how are you structured? Do you have a team? Do you have teams of people that are searching for this? Is this on a much smaller scale where you're just looking for one really large market? So it's essentially like you and one other person going out and talking to people. How do you actually do this as a corporate strategy? How do you do it?
Yeah. So I'd say, how we think about the work that needs to be done, we're really focused on the impact of the technology. What problems can we go solve? But then, as you mentioned, we have to really understand, those specific problems and verify that quantum computing will be a good solution to that. And so we, have experts on the team who are inventing and coming up with these quantum algorithms. But in order to really understand the speed up, we need to write those algorithms down in code. So it's, we need to write out the program. It's really hard to know if your program's going to run if you were to write your code down on paper. It's hard to debug. It's hard to know if you get the right answer. And so we need, a programming framework to be able to verify the speed up. And so, as I mentioned earlier, it's the inputs and outputs, because quantum computers are going to be slower. The clock rate is going to be slower. It's all of the gate operations that are happening. And so doing that translation of, let's say an academic algorithm that someone's come up with and said, this algorithm has an exponential speed up. But that algorithm, that exponential, there's this academic notation with this curly O in front of it, which means order of. It's order of, exponential speed up. But that can have a large constant prefactor. So you may think you have something that would run in an hour or a month, but if the constant prefactor is a billion, it's going to have a really long runtime. So we have that work that's done to write that algorithm down in code and know the runtime. And so we've developed tools and capabilities. We've developed the language. We've developed tools on resource estimation, just because, if you think back to when, the first programs were written, we didn't have those tools and capabilities and understanding of how code works. And so today we have tools where we can know how long a runtime will be for an algorithm that will run on a quantum computer that we don't have yet today, that we might have in 5-10 years from now. But we can do that coding work now, which is really, really impactful. So then that tells us, okay, for a specific, let's just stick with this chemistry algorithm that I talked about for carbon fixation. So we say, okay, we've got that runtime measured, but our first cut at that runtime might say, oh, it'll run in 400 years, which is a great improvement from the classical algorithm that maybe was billions of years. So we've gotten it down to hundreds of years, but most of us want results faster than that. And then we can do that, that computing work. So it's a set of skills on writing good, fast code, high performance computing. Where can we parallelize? Really understanding the details of those algorithms. And now we've gotten that down into saying, okay, now we know that we can solve that in 1 month if we had a quantum computer that looked like this. So that understanding of the problem the runtime of the algorithm, that gives us insights into what hardware that we need. Now we say, okay, we need qubits that stay quantum long enough. We need gate speeds that are fast enough. We need to, have something that's reasonably sized that we can actually manufacture. So if we're doing this at super cold temperatures. So if we had a qubit technology with a physical dimension such that with the millions of qubits that we need is the size of a football field, that's going to be really hard to make cold enough and have the engineering infrastructure around that. So that's, really informed the decisions that we've made for the qubit technology that we're working with. And so we're taking a really different approach to that fundamental building block, the qubit. And we're using what's called a topological approach that protects the quantum information. And so we've got our team, going back to your question, we've got our team structured along all of these elements. So there are people who have deep understanding of the physics of quantum systems and condensed matter systems that are designing these qubits. We have, teams that are growing the materials and fabricating the devices. It's a, strong feedback loop as we, validate what we're building in the lab with the theory and simulation. We've got teams that are building these measurement and control capabilities. So one of the announcements that we've been talking about in the last year was a team in Sydney, Australia, that's designed a cryogenic CMOS chip that can control up to 50,000 of these qubits with just 3 wires running up to room temperature. So that's an important element because information carries energy. And how do you control this from a hot, noisy data center? And how do you get information in and out of that without disturbing the qubits? And then we've got folks thinking about, all of the software stack. And so, runtime, compiler, language. And we've got teams working on, okay, if we want to make this accessible to customers, it's got to be a cloud service. And what are the tools and capabilities that we can put into developers' hands to build that? And so, that's really how we have our team structured across, all of these elements of the stack that are required. And then, of course, because we're doing all of this in parallel, that gives us rapid feedback mechanism so that we are, really efficiently designing and building these systems.
I was talking with John. He's the founder of Blackpoint. And what they do is pretty cool. They do like cybersecurity, but like nation state grade, like NSA guy, very, very cool stuff, right? Had to cut a lot of interesting information out of that podcast. But there is a lot of talk about like quantum and security, specifically with encryption around Bitcoin. And I was curious, like, when will I be able to use a quantum computer to steal all of the Bitcoin?
So, that's abstract your question a little bit. So that's, top of mind for a lot of people, top of mind for us at Microsoft is that one of, you talked about, quantum and encryption, and one of the early algorithms that was designed for a quantum computer is Shor's algorithm that does large prime factoring very, very fast. And so that's an example of this, this algorithmic approach. Or classically, that's factoring large prime numbers is really hard for classical computers to do, or figuring out the 2 large prime factors that go into, an RSA key or, elliptic curve algorithm. And that's something that quantum computers are really, really good at, it turns out, exponential improvement in speed. But this goes back to something that we talked about earlier, which is quantum computers are not going to be good at everything, which is, you could say, well, that might be disappointing for some, but it's actually good news for encryption. If you think about these systems and, the way that we communicate in the world, it's a good thing because we can pick another, encryption protocols are based on hard math problems and the hardness of that math problem for all of the computing technology that we have. And so this is an area, well, you may be excited to crack Bitcoin and use this. We actually, we want to live in a world that's safe and secure and we can encrypt our information. And so there are, we and many teams around the world are working on what we call post-quantum cryptography. So, quantum cryptography that will be robust to quantum attacks from these systems. And so that's where, I feel reassured that we have viable solutions in place already today to protect us from quantum attacks. And these are classical algorithms. So that's another, it's part of this relief that quantum computers will not be good at everything. We can use different classical protocols that we believe are secure from quantum attacks to encode our information.
I was hoping you'd give me a different answer.
I know you were.
No, I talked to the creator of Ripple, which is one of the popular cryptocurrencies, XRP, and he was explaining to me that he has a 10-year horizon, so he doesn't think it's a problem within the next 9 to 10 years. So they're not allocating resources currently to be solving this problem. He also explained that there is algorithms that are very susceptible to being cracked by quantum computing. And then there's also quantum computing resistant algorithms. So he explained to me that there's these differences out there in the marketplace. And he says at any point in time, if something happened, we could just switch it. The problem is the quantum resistant algorithms are slower. So for transaction speed and things of that nature on the network, it's just a slower process. So they're using the current traditional one. So that really took this big cloud mystified thing that I had researched for hours online, seeing all these different opinions, and you just drill down, you get to the expert, and they just explain it to you like you're a child. And I was just like, thank you so much. But I was hoping Julie would tell me, we've got something secret at Microsoft, Joel, and all the Bitcoin is yours.
No, he's right about that. And there's these, different cryptographic protocols, and they have different trade-offs. It's absolutely right. Some of them are slower. They might take more compute resources. The key size changes. And the thing we don't know. I think that 10-year time frame sounds about right. You need about 4,000 really high quality qubits. And so with every qubit technology, you'd have to do some level of error correction. So the number of physical qubits you need is orders of magnitude larger than that. So this is going to be a really big system that's needed for that. But the issue with, I think we don't want to wait until somebody has that system in place for a couple of reasons. One is that anything you're encrypting now, it's you have to think about what's the security lifetime of the information that you're transmitting. And so, if you're thinking about your Bitcoin, your encryption around your Bitcoin or your passwords, those are, relatively easy to change, but we don't want those out in the open. If somebody had this technology and could decrypt them tomorrow, we want something that lasts longer than that. But if you had really secret information like health information, or you talked about nation state security, things like this, you think about a security lifetime of that data being much, much longer than that. And so if it's longer than when you think this information could be cracked, you actually need to start thinking about that now. Because you could think of, someone who you wouldn't want to have this data fall into their hands, just recording it and saving it so you could crack it later. So it is important to think about it now. And then the other factor, so the first one is, that lifetime of the data that you want to protect and how long you want to protect it for. And then the second is, how long will it actually take you to switch? And so, I think about, as we talk to CTOs and, leaders who are concerned about security, do you have the cryptographic agility to make that switch overnight? And as we think about, building these systems, building them in with that cryptographic agility to be able to change quickly is important. And then, of course, I guess maybe I'll add a third one, which is you want to have time to test, of course, any system that you're putting in place.
There we go. I was talking with Tony. I think his last name is Utley, Tony Utley from Honeywell, I think like last summer. But I saw that you had a partnership with them on the website. So I went and I looked at like the free trial and everything. And then at the bottom, you had your partners and you had Tony. You also had Trimble on there. You had a bunch of partners. I kind of went into a rabbit hole like, oh, I know all these people. It's just so cool just to get to see them and to see everyone working together. It's weird because it's such a large world. It's such a large community, but it's also very, very small. I think earlier you were saying quantum computing's like that too. Mm-hmm. How did this partnership happen, and what is this partnership with Honeywell?
So the partnership with Honeywell is all around Azure Quantum, and it's putting these tools and capabilities in people's hands. And so this came from, we've been in conversation with Tony and the team for a long time, and we're building our end-to-end quantum computer with this really different hardware and the programming framework, coding language. Of course, we have the Azure infrastructure. And in conversations with our customers and partners like Honeywell, it's, we really believe that it's important to, put all this technology in the hands of developers and researchers worldwide. And it was, felt really natural for us to work together on this of, combining this, the quantum technology that Honeywell is building with the programming models and frameworks and cloud infrastructure that Microsoft is building. So we're super excited about the partnership with Tony and his team, and combining these capabilities into this open ecosystem. And then this all goes back to the impact that we want to have with this technology. You think about problems, in chemistry, material science, hard optimization problems. It really takes building a global ecosystem of different players in the industry to not only build the technology that's required to solve these problems, but to understand all of these use cases and problem areas. And we see that as super, super important. We don't know where these developments are going to come from. And so it's really important to put this, put these tools and capability into the hands of people like you and developers and researchers all over the world, and put that together with, the quantum hardware that's available today. And the beauty of that is you can, we talked about resource estimation and being able to understand the runtime of a quantum computer that we don't have yet. Well, we have this, we've built a high level programming language. So you can do that programming. It's abstracted away from the hardware. And what that gives you is a programming language that can run on the quantum computers that we have today from players like Honeywell and IonQ. They're going to continue to evolve those systems and grow. And you can run that code across multiple different systems and, multiple generations of, say, the Honeywell machine. And so they've got their H0 machine in Azure Quantum. They've introduced the H1 machine, which is the next evolution of that hardware. And you can have that single Q-sharp program that gives you, durability of your code. And you can, run that on larger quantum systems, higher quality systems as those become available. So we see that as really, really exciting, bringing, different partners in the industry together with our tools and capabilities and making that available to the brilliant minds around the world that are going to go figure out how to solve these tough, interesting problems with this technology.
So we can go on there right now and go and just download this programming language or do it in the cloud and actually write some code, run it on a quantum computer. I could select if I want to run it on Honeywell systems or this IonQ, I think you said.
Mm-hmm.
I can choose. And from what I understood when I talked to Tony is that these different technologies, because there's a couple different companies out there, they're doing quantum computing, but they're using different underlying technologies to do it. And they have little pros and cons and differences. So this type of quantum computer might be better in these areas. Is that correct or is that not correct?
That's roughly right. And so there's a set of requirements that we've known for a long time, actually, of what it takes to have to build quantum bits, let's say, or have a quantum computer. You need to have, some quantum 2-level system that you map to your zeros and ones. You have to be able to control it. It has to stay quantum long enough to do something interesting. So we have a general idea, but there's different underlying building blocks that people are using to build this technology. We're building topological based quantum bits. People are using building superconducting qubits. Honeywell's building trapped ion systems. And so there's different flavors of these, and they have different characteristics. There are different error rates of the qubits. So how fast they lose their quantum information. It's kind of a shorthand way to think about it. What's the gate speed? Tony's system is controlled by lasers. Some are controlled by microwave pulses. And so there's these different pieces. And so your control systems look different and how you engineer these systems. And, it's super exciting to be able to then put these different types of technologies together, just in your Azure portal for developers to then go try and use and test and learn from.
Excellent. Where do they go to do that?
Azure.com/quantum.
There you go. You nailed it too. I was like, oh no, I just put her on the spot.
No, I know. It's exactly where you go. You get Azure to do it.